Using the quotient rule, when we see x cubed divided by x squared, we're going to use the thinking that this is x to the 3 minus 2 or x to the first. Since we know that x to the first, nothing's really happening, this is just equal to x for our final answer. In the second problem, we're going to use the quotient rule as well, but notice we have an extra y. There's a couple different ways you can think about this. Option 1 is to strictly apply your rule. So when we have the same base, we can use the rule. So this is x to the 2 minus 3. The y is not subtracting anything because there's only one variable with a y. 2 minus 3 is a negative 1, so I have x to the negative first times y. And we know that x to the negative first means to take the reciprocal. So this is 1 over x times y. Here this looks like multiplying a whole number by a fraction. So we can think of that whole number being over 1, so that we know we can multiply straight across the numerator and straight across the denominator. Option 2 looks a little bit different. Personally, this is the way I do the problems. I think of a negative exponent as meaning that something is not where it wants to be. And therefore, when I look at the original problem and I see that there are more x's in the denominator than in the numerator, I know my x's are going to stay in the denominator. When you do that, you can always do the large number minus the small number because you're automatically putting the x's where they belong. The y never moves out of the numerator in this method, and we have y over x to the first or just y over x. Either method of thinking about it yields the same answer. I'm going to use the second way of thinking about it when I do this next problem. I can see that there are more x's in the denominator and more y's in the numerator. So my y's will be in the numerator with y to the 4 minus 3, and my x's will be in the denominator with x to the 4 minus 3. In both cases, 4 minus 3 is 1, so I have y to the first over x to the first, or just y over x. Skipping down to the next row, we see that we now have some coefficients as well as variables. When I see 20 over 2, I treat it the same as reducing any other fraction. 20 divided by 2 is 10, and since the larger number was in the numerator, I'm going to have a 10 in the numerator. Just with some previous problems, there's more than one option for how to do this. You can strictly apply your rule, or you can think of the negative exponents as meaning that things aren't where they want to be. If you use that second way of thinking about it, the x cubed is happy where it is because it's already a positive exponent. But this x to the negative second in the denominator wishes it was in the numerator, so we can move it up. The y to the negative second from the numerator wishes it was in the denominator, so we move it down. And the y cubed from the denominator wishes it was in the numerator, so we move it up. So this is option 1 for how to solve. From here, we can then apply our rules. The 10 doesn't have anything else to do at this point, but x cubed times x squared is x to the 3 plus 2. When we look at the y's, we see that there are more y's in the top than in the bottom, so they're going to stay in the top, and we're going to have y to the 3 minus 2 because those are dividing. Notice we now do not have a denominator because everything came out of the denominator. So our simplified answer is 10 times x to the 5th, y to the first, or just y. Option 2 for how to think about this is to strictly apply the rules. You're not moving anything anywhere. You're just thinking it straight through. Again, we would say that 20 divided by 2 is 10. But now we would say this is x to the 3 minus negative 2 because we have a 3 in the numerator and a negative 2 in the denominator. And then we would have y to the negative second minus a negative 3, again because you have negative 2 in the numerator and negative 3 in the denominator. Then you need to use your rules of integers. So I have 10 times x to the, remember, minus a negative is really the same as plus, so 3 plus 2 is 5. And negative 2 plus 3 is really just 1, so that's just a y. You get the same answer either way, so whether you prefer option 1 or option 2, it's really your choice. In the next problem, I will make the recommendation that when you have a negative exponent on a fraction, you think of that as being two separate things to do. So first I have to take the reciprocal, then I have to square. So let's write ourselves a note. The negative means take the reciprocal, and the 2 means to square. But before I go to do that, I take a peek inside those parentheses and I see we have the same base in the numerator and in the denominator. We have x cubed and x squared. So let's actually tackle the inside first. You know from your order of operations that you should do what's inside the parentheses before you try to do anything else. So x cubed divided by x squared is x to the 3 minus 2. And we know that x to the 3 minus 2 is just x to the first, or x. So it's really just x that's being raised to the negative second power. Now we can think about the whole reciprocal and squaring business. This is 1 over x squared because the negative tells us to take the reciprocal and the 2 is squaring the x. In our next problem, it becomes really important that we simplify inside the parentheses before we apply the square. Notice you have an x cubed and an x to the 4th. I prefer the method where I think about where are there more. There are more in the denominator, so I'm going to say, okay, this is x to the 4 minus 3 in the denominator. For the y's, there are more in the numerator, so it's y to the 4 minus 3 in the numerator. And then I'm keeping track of the fact that that whole thing is being squared. Y to the 4/3 and x to the 4/3 each remain as a power of 1, so I have y to the first, or y, over x to the first, or x, and that whole thing's being squared. And now you're ready for your quotient rule. When you raise a quotient to a power, you know that each part is raised to the power. So we're going to have a y squared divided by an x squared as our final answer. Moving down the page, we have a number involved in here in addition to having a variable. So using your quotient rule, you know that this is 3 to the 4th divided by y cubed to the 4th. So this requires us to do a couple of things. First, we're going to have to raise 3 to the 4th power because that's a number and we always want to do that math out. In the denominator, we're using the power to a power rule. Y cubed to the 4th means I need to multiply the 3 and the 4, so we have y to the 12th. In our next problem, thinking of this as two separate exponents really helps. This part tells us to take the reciprocal, and this part tells us to cube. So I'm going to take the reciprocal first and say that this is now 3/2 just being cubed. That lets me use the quotient to a power rule and raise both the numerator and the denominator to the power. We know that 3 cubed is 27, and that 2 cubed is 8. So our final answer is 27/8. We can even apply this thinking when we have a number in scientific notation. This is a product to a power, but it's also using the power to a power rule. So first of all, we have 6 squared times 10 to the 4th squared. We know that 6 squared is 36, and 10 to the 4th squared means we multiply 4 and 2 to get 10 to the 8th. When we look at this number, we realize this is not in scientific notation. We're going to have to make the 36 into a 3.6. Moving that decimal point one place makes the number smaller. To balance that move, I need to make the power on the 10 one order of magnitude bigger, so I've got a 10 to the 9th. We see some quotients also with scientific notation, and just like we did with the products, we can do the division first and apply our rules as we go. So 4.8 divided by 1.2 is an awful lot like 48 divided by 12, and we know that to equal 4. So this is going to be 4 times 10 to some power. Using our division rules here, we see 13 and 9. 13 minus 9 is 4, so this is 10 to the 4th. We check to see that it's in scientific notation, and since 4 is just one digit in front of the decimal, it is, so we're done with that problem. 5.6 divided by 7 is just like 56 divided by 70. So we could do that as a fraction, but since with scientific notation we're going to give our answers in decimal, it does in this case make sense to go ahead and divide, and you see that you've got 0.8 when you do 5.6 divided by 7. For our powers, we have -3 minus a -9. Now we know that minus a negative is really plus, so -3 plus 9 is 6. So the power on the 10 is 6. But when we check to see that our answer is in scientific notation, we see that it's not. In this case, the decimal point needs to move one space to turn this 0.8 into an 8. That makes the number bigger, which means that our power on the 10 needs to get smaller by the same amount. So we have 8 times 10 to the 5th as our answer in scientific notation. We have a word problem. The speed of light is about 3 times 10 to the 8th meters per second. How far would a beam of light travel in 8.64 times 10 to the 4th seconds? Well, if you think of your typical distance equals rate times time, we're given a speed, so that's our rate, and we're asked how far in a certain amount of time. So we can see where everything goes in the problem. We can see that we need to take this speed, we need to multiply it by this amount of time, and that will give us how far this beam of light has traveled. We can break this down and multiply the 3 times the 8.64 because they're like the coefficients of the powers of 10, and we have 25.92 times 10 to the power. Now when we look at this, we have multiplication, so we know when we multiply with the same base, we add the exponents. 8 plus 4 is 12, so we have 25.92 times 10 to the 12th. But we always check our answers when we're working with scientific notation to make sure they're still in scientific notation. And we see that the decimal point would need to move between the 2 and the 5 to be scientific notation. Since we made that number smaller, we need to make our power bigger in order to balance that out. So the distance will be 2.592 times 10 to the 13th meters. Don't want to forget the units when we're doing a word problem. All right, now we're doing a combination of all of our laws of exponents, but continuing with scientific notation. Notice here we have a power being applied to the whole number. I'm going to rewrite the first number just like it is, 7 times 10 to the 3rd. But this one tells me I have to take the reciprocal of 4. Now we know that the reciprocal of 4 is 1/4, and that as a decimal, that's 0.25. So we have 0.25 times 10 to the negative 7th, because we're using the power to a power rule. Multiplying the 7 by the 0.25, we get 1.75. And multiplying 10 to the 3rd by 10 to the negative 7th, we're going to add those exponents and get 10 to the negative 4th. Checking to see that we're in scientific notation, we see that we are because there's just one number in front of the decimal point. In the next problem, we see that this portion has the power to a power rule going on. So we need to tackle that part first. So we see that we have 4 squared and 10 to the 5th squared. Well, we have 10 to the negative 7th times, because we didn't do anything with that. 4 squared is 16 times 10 to the 10th, because 5 times 2 is 10. We know with the commutative property, we can multiply in any order we want to, so that 16 can come first, and 10 to the negative 7th times 10 to the 10th will be 10 to the 3rd. Since when we multiply with the same base, we add the exponents. Checking, we see this is not in scientific notation. We need to move that decimal point in between the 1 and the 6. Since that made the number smaller, we need to make the power larger. So we have 1.6 times 10 to the 4th.